Okay, good morning. Okay, in the last class we have started laser beam machining. We have discussed the basic mechanism, how the laser being used for cutting operation or drilling operation, or what is the basic principle behind the laser beam machining. And we have seen various advantages, disadvantages, and applications in laser beam machining. Now coming to the mechanism of material removal. So we know the basic principle, that's the same thing. Anyway, we will see the mechanism of material removal, how the material is being removed. So this is the basic setup you have already seen in the laser beam machining. Here the tool is the laser beam, or the material is being removed by the heat produced by the laser light or the laser beam, which creates the or increases the which is being highly focused to a small area that may increase the temperature and vaporizes the metal, thereby material is being removed. So as a mechanism, we can say, first of all, the focal point, as you can see in the figure, focal point of the lens is so adjusted that the laser being focused to a particular point where the machining is to be done. You can see the focal length. We can adjust it by adjusting the focal length. Then the workpiece is being cut, and the machining or the machine axis can be moved using the CNC controls, various CNC controls. Now, in order to clear the molten metal, or the, you can see whether when the machining is done here, there will be certain vapors coming. So these vapors has to be prevented, or it should be cleared off. So in order to clear off that, some gases under the pressure will be passed to the area, or this localized area. This is the basic mechanism of the material removal. So mainly the material removal is being done by increasing the temperature in a localized area. As you can see here, how it is being done by focusing the parallel coherent laser beam to a highly localized area, a small area where the temperature is being increased or rise. There will be a rise in temperature, due to which the metal at the portion will be melted, and the molten metal, or it gets vaporized, and it will be cleared off. So this is the mechanism of material removal in LBM process, or laser beam machining. Now, like other cases also, we will see the what are the factors which affect the MRR in the heat affected zone or quality, anything. So we will see the factors, which are the factors which affect the MRR, HAZ, and quality. So mainly the cutting performances, various cutting performance are there. That is the material removal rate, quality, surface quality, heat affected zone, etc., etc. These are these can be manipulated, or this can be changed or altered by certain process parameters like laser power. There is a laser power, by laser power, laser power, then cutting speed, assist gas pressure, assist gas pressure. That is, we have already seen there is a gas, extra gas is being given to the area where the machining is being done in order to clear off the vaporized metal portion. So the assist gas pressure, the pressure of that gas, then focus position, where it is focused. So these are the controllable parameters mainly used in order to alter the qualities or MRR or HZ, anything. So we will see one by one each effect. First one regarding the material removal rate. So regarding material removal rate, how it is being altered. So there are many parameters through which the material removal rate can be altered. That is, first case is the beam related parameters. That is the parameters which are related to the laser beam. Then there are some process parameters and also something, some parameters related to the workpiece material. So one by one we will see. First of all, the beam related parameters. These are the parameters which are related to the beam. First one, beam power intensity. Beam power intensity. So as a beam power intensity or the power intensity of the laser beam is increased, then the MRR also will be high. So the first one is the beam power intensity. The next power parameter is the beam geometry. Beam geometry. The geometry of the beam. What is the shape of the beam? Whether it is a circular or and in any other shape. The geometry of which, the dimension. Then the diameter of the beam, how it may affect the material removal rate. Then comes the wavelength of the beam. So the wavelength of the laser beam. So for different lasers, there are different wavelength. So short wavelength. If the wavelength is short, then the MRR will be high. Likewise, these are the main parameters which comes under the beam or the beam related parameters which affect the removal rate, material removal rate. So there are certain parameters, there are many parameters which will affect the, or the variation of which will affect the material removal rate. So so in that, the first classification is the parameters which are related to the beam or the laser beam. There comes these four things, that is the beam power intensity, beam geometry, beam diameter, and finally the wavelength. Now the process parameters. What are the parameters which are related to the process, that is the laser beam machining process? That is, first one, spot size. If it is being focused to a small spot or the spot size is small, then the material removal rate will be high. And if it is in the other case, it will be small. Then the position of the focus, regarding the position of the focus, regarding where it is being focused, whether it is underneath the workpiece or just beyond, or the focus position or the focal point is above the workpiece or below the workpiece or at the surface of the workpiece. So depending on the focus also, the material removal rate changes. Then regarding the gas pressure, there is a gas pressure, that is a gas, assisting gas given, the pressure of which will change the MRR. that is with more gas pressure, then MRR will be also more. And regarding the cutting speed, so these are the basic process parameters, or the parameters which are related with the process, which affect the MRR. And finally, one more, that is a workpiece related or material related parameters. That is, first one, melting point of the workpiece, then the composition of the material. What is the composition of the material? Then reflexivity, specific heat, thermal conductivity, latent heat, etc. So the last four things that is given here. So as this value, that is reflexivity, specific heat, thermal conductivity, latent heat, etc. When these values becomes low, then it will increase the MRR. MRR will be high. So these are the main factors which affect the MRR. Three cases were there. First one, the beam related parameters. So these were the parameters which comes under the beam related parameters. Then comes the process parameters. And these are the process parameters which affect the MRR. And finally, the parameters which are related to the workpiece material. Okay. Now, you will see the effect of the heat affected zone, or the before that, the material removal rate, the values for the any LBM or the laser beam machining, the cutting speed can be as high as 4 meter per minute. That is, the cutting speed is given as 4 meter per minute. This can be achieved through LBM process. And the material removal rate, MRR, is typically the average value is 5 millimeter cube per minute. And the dimensional tolerance possible value of the dimensional tolerance is between plus or minus 0.015 to plus or minus 0.125 mm. This range of dimensional tolerance is possible. And finally, regarding the surface finish, it is between 0.4 to 6.3 micrometers. Now, regarding the heat affected zone, so we have already said that this is highly localized or highly focused operation. So even though temperature is being generated, usually in any cases, in any machining process where the temperature is involved, there will be, or there should be, some heat affected zone. So in this case also there is a heat affected zone, but comparatively it will be less because this is highly localized. Now, how it can be altered, or how it changes due to various process parameters, that we will see. First of all, the laser beam power. With the laser beam power, there is laser beam power. Okay, laser beam power. So as the laser beam power is increased, so when the beam power is increased, the temperature is increasing. So as a result, HAZ will also increase, or the heat affected zone will also increase. Now, similarly, with pulse frequency, so it is being done by pulses. So if the pulse frequency increases, HAZ also increases. Now, what we can see is regarding the laser beam diameter, whether it is small or high, this is not depending on the HAZ, or it has no effect on the heat affected zone. So the laser beam diameter diameter has no effect on the heat affected zone. And also the heat affected zone depth, this is increasing with the thickness of the workpiece. Regarding thickness of the workpiece. So as the thickness of the workpiece increases, heat affected zone depth also, the depth at which the heat affected zone is there, you can see here, depth of the heat affected zone also increases. Now what happens if the cutting speed is increased? If the cutting speed, you can see, when the cutting speed is increased, what happens is the time of engaging the tool or the laser beam at a particular point is decreased. That means it is not placed full time, it is only for a short time the laser is being in contact with the particular portion, or the time of contact of the laser beam with the workpiece got decreased when the speed is increased. So as a result, what we can see is the heat affected zone will be lower, or narrow heat affected zone will be there. So these are the main effects of various process parameters, or the parameters with heat affected zone. First of all, regarding the laser beam power, when the laser beam power is increased, heat affected zone also increases. Then regarding the pulse frequency, when the pulse frequency is increased, heat affected zone will also increase. Then regarding the laser beam diameter, the laser beam diameter has no effect or negligible effect on the heat affected zone. And we have seen this heat affected zone increases with the thickness of the workpiece. And finally, regarding the cutting speed, as the cutting speed increases, what we can see is the cutting time decreases, and finally it will result in the narrowing of the heat affected zone. So these are about the heat affected zone. Now regarding the quality produced, or the tolerance, surface quality or tolerance, what is happening? We can see that is first of all, the focus position. Focus position is the significant thing which affect the quality. If it is focused to the surface, then it will have a quality. If it is focused beyond that, then there will not be a certain quality, or the quality may lose. Or if it is so in order to have a good quality, it has to be focused to the right position. So the focus position is the main thing, or a most significant parameter which affect the quality. Then regarding the feed rate at which the tool is being fed. Here, what is the tool? Here the laser beam. So the rate at which it is being advanced, or it is being fed to the workpiece, if it is increased, or the feed rate is increased, then it will generally, as a general trend, it will increases the surface roughness, or the surface quality may deteriorate, or the surface quality becomes less When the surface quality is less, we can say the surface roughness is more. So as the feed rate is increased, surface quality decreases or the surface roughness increases. Now regarding the cutting speed. Cutting speed. Cutting speed. So what happens if the cutting speed is increased? So when the cutting speed is increased, then the surface roughness decreases. If surface roughness is decreased means that is the surface quality is increased. So this is a direct impact, that is a or directly proportional, we can say, that is a, as the cutting speed increases, surface quality also increases. Next, regarding the power density. Power density. Okay, power density. So by increasing the power density, the roughness also increases, or we can say the surface quality decreases. So these are the main things. That is, first one regarding the focus position. Second is the feed rate. That is, by increasing the feed rate, that will increases the surface roughness or it will decrease the surface quality. Then regarding this cutting speed, as the cutting speed increases, the quality also increases or the surface roughness will decrease. And finally, the power density. By increasing the power density, it will increases the roughness or it will decreases the quality. So we can see the surface roughness values. That is surface roughness. Surface roughness of the value. Surface roughness values as 0.4 to 6.3 micrometer RA value. And the tolerance between, we have already seen tolerance value between plus or minus 0.015 to plus or minus 0.125 mm. Okay. So these are all about the laser beam machining. Now we will start another machining process, that is the electron beam machining. So first of all, we have seen laser beam machining, where the tool is or the tool is the laser beam, or the machining is done by using the laser beam. And how it is being machined? That is using the energy produced by the laser beam. It is being converted into heat energy or thermal energy, which melts and evaporates the metal and gets removed. Thereby machining is being done. Now regarding the electron beam machining, how it is being done. Here, this is also a material removal process or the metal removal process, where a high velocity electrons or high velocity focused electrons, stream of electrons or beam of electrons are used to machine or remove the material. How it is being removed? This stream of electrons or high velocity electrons will have some kinetic energy, and this kinetic energy is transformed into thermal energy. So as there is a thermal energy, like in the case of LBM or laser beam machining, when the temperature is increased, the metal at the portion will melts and evaporates, and we remove this vapor, thereby machining is being done. So this is the basic procedure or the basic mechanism of electron beam machining. So what is being done, or what is a electron beam machining? This is the metal removal process by which high velocity focused stream of electrons are used. So here also focused, high velocity focused electrons. So the electrons emitted by the cathode. Here also you can see in the figure, this is the setup. Here the electron gun, this is the electron gun, which is connected to the cathode. This is kept as a cathode, and here you can see a grid cup. Here, using this cathode, a high voltage is being applied, and as a result, the electrons are emitted, which is focused, highly focused, or accelerated using the anode, and it is being focused by the magnetic lens and other medium focusing objects. Using that, it is being focused. This you can see, this is the electron beam which is focused, converging. You can see it is converging. So it is highly focused to a small area where the workpiece is being kept. This is the workpiece. This is the workpiece. So it is being highly focused to the point where the machining is to be done. So as a result, the kinetic energy of the high velocity, what do you say, the electrons, it is almost 50 to 80% speed of light. So these electrons are impinging on the workpiece with the 50 to 80% of the speed of the light. So at that particular speed, it will be impacting on the workpiece. So as a result, what happens is the kinetic energy is being converted into thermal energy over here in this small portion, and the metal will be molten state, or it will become then vaporized and will be removed. So this is the basic mechanism of the electron beam machining. So before going further, you will see a animation.
Electron beam machining. Electron beam machining, or EBM, is a non-conventional machining process used for machining of very hard and brittle materials, which otherwise cannot be machined by conventional processes. In electron beam machining process, the kinetic energy of the electron is converted into heat energy by impinging the fast-moving electron on the workpiece surface. This heat energy evaporates the workpiece surface, similar to the laser beam machining process, where a laser is used in place of electron beam. If you are interested in knowing how laser beam machining is carried out, I have provided the link in the description below. Click on the I button to watch it. And if you are new to ADTW, click on the subscribe button below. This video will cover the following about the EDM process. 1. Working principle. 2. Construction. 3. Working. 4. Application. 5. Advantages and disadvantages. Working principle. This machining process works on the basic principle of conversion of kinetic energy of electrons into heat energy. When a high-speed electron impinges on a workpiece, its kinetic energy is converted into heat energy. This heat energy is used to vaporize material at the workpiece interface. This is the basic principle of EBM machining. This process is carried out in the vacuum, otherwise the electrons will collide with the particles in the air and lose its energy. Construction. Construction of electron beam equipment is built similar to electron beam welding machines. Power supply. Electron beam machines utilize voltage in the range of 50 to 200 kV to accelerate the electron to 50% to 80% of the speed of light, which is about 200,000 km per second. Electron gun. It is a cathode ray tube which generates the electrons, accelerates them at a very high speed, and focuses on the required spot on the workpiece. Cathode filament is made up of tungsten, which is heated at about 2500 degrees Celsius, which accelerate the electron emission by thermionic reaction. Anode. Anode is connected to the positive bias. The electrons are pulled towards the anode at very high. For electrons produced by the cathode filament are not diverged from its path. Magnetic lenses. The emitted electrons are both divergent and convergent. The magnetic lens reduces the divergence of the beam and allows only convergent beam to pass to the next stage, thus, a highly focused beam of electrons is obtained. Deflecting coil. The deflecting coil does not allow the beam to deflect, thus forming a high-intense beam. Workpiece holding device. The workpiece is held rigidly on the workpiece holding device, which can move in all three directions, that is, in the X, Y, and Z axis. Working. When a high voltage supply is applied to the cathode filament, it generates the electrons. These electrons move toward the anode at very high velocity. After passing through the anode, the beam of electron is made to pass through magnetic lenses, where diverging and low-energy electrons are absorbed, and only converging beam of electron is made to pass through it, thus forming high-quality electron beam. Then this beam passes through the electromagnetic lens and deflecting coil, which focuses the high-energy electron beam onto the required spot of the workpiece surface. The high-intense electron beam impinges on the workpiece, where kinetic energy of electrons convert into thermal energy. And the workpiece material is removed by this intense heat, thereby melting and vaporizing it. And this whole process is carried out in the vacuum chamber. Application of EBM. 1. EBM is mainly used for micro-machining operations on thin materials. These operations include drilling, perforating, slotting, and scribing, etc. 2. It is particularly useful for machining of materials of low thermal conductivity and high melting point. 3. For making fine gas orifices in space nuclear reactors and gas turbines blades. 4. Flow orifices in wire drawing dies. 5. It is particularly suitable for producing very small diameter holes, about 0.002 millimeters. Advantages of EBM. 1. Very hard and heat-resistant materials can be machined. 2. Close-dimensional tolerance can be achieved. 3. Produces good surface finish. 4. Heat-affected zone is minimum. 5. No physical contact between tool and the workpiece, therefore, there is no tool wear. Disadvantages of EBM. 1. Metal removal rate, that is, MRR is low. 2. Vacuum requirement limits the size of the workpiece. 3. It can be used for small cuts only. 4. Equipment cost is high. Hope you have understood electron beam machining process. If you are new to ADTW,